time, we were seeing how we can derive some compositionality observation of how behaviors of component systems relate to behaviors of composite systems in these double categories of lenses. The same lessons will work just as well in other kinds of double categories of systems. But in order to really get multiple systems interacting together, we're going to need this symmetric monoidal structure on our double category. So the main thing we're going to talk about this time is our symmetric monoidal double category of systems. And well, it's not really of systems, maybe I should say, symmetric monoidal double categories. We'll just say that. You might say of systems, or maybe of control systems. But okay. So to recall where we were last time, we had our special clock system, which, as we see, this is the clock, and it is a loose morphism in the double category of lenses. But this is specifically lenses for vector bundles. And then what we saw is that if you had any system of ordinary differential equations, right, you could first pick here a choice of observation and parameter. And then if you had a map here so that this commuted, this is exactly what was meant by a trajectory system. And as you can see, this is a square. So let me give some other examples, right? If we take lenses just in set, so simple lenses, and here we take the natural numbers, and here the natural numbers and no input, and then here we take the identity down here and +1. So this is now our discrete clock. Right? Now, if we take any more machine like this, here is a choice of two sequences, a sequence of outputs and a sequence of inputs. And then here would be a sequence of states. And for this to commute would precisely mean that S of n plus 1 is equal to U of Sn In. And Sn, if I expose it, I get On. Right? We can actually go further, and I think I'll save this for another time just to make sure I'm really fresh on actually the construction. It's due to Owen Lynch, jointly with Igor Rischel and Sam Stanton and myself. But as you can tell, I need to refresh myself on it. There is also a discrete time stochastic clock, which will represent random variables which update according to the law of a Markov decision process. And so this is also quite nice, but I think I'll save that for next lecture as sort of a fun takeaway that these continue to work for even more kinds of systems, and that way we can go over, because that requires a bit of background in probability that I would actually like to cover in the lecture. So there's these things, but now also these were in lenses, in lens set, but also we could have other situations. So let me talk about in cospan, right? So in cospans, let's say cospans of let's just say cospans here of labeled graphs. Right, as we discussed, we could consider a labeled graph as a cospan. From the left leg being empty, we should have our graph G, or I'm going to draw this a little differently, excuse me. A labeled graph graph G, and then we have some kind of boundary here, right? So imagine that this graph was, say, it's a labeled graph, so it has some kind of underlying graph structure, and the edges, let's say, are labeled with a fixed labeling alphabet, something like this. And the boundary could be something like these 2 points here, mapping in to this. Right? So now I want to articulate, we saw before, if you remember a few lectures back, that paths or of labeled transition systems or traces of labeled transition systems were representable. Maybe I should put a few more things over here, and let me take all 3 of those inner ones here, just to have a little more going on. So this is G, this whole thing. And this is boundary G, and that's the map. So now, if I have up here, I could take a path for any word. So for any labeled graphs, let's say labeled in a labeling set L, for any word, W in L star, so these are just words, as in sequences of elements of things in L, we can form the path PW. I'll put it like this as well. And then the boundary of PW is going to be just 2 points, which I'll call start and end. And they include here. And PW here is going to be equal to start. And then we go, the first thing in the word, the second thing in the word, ... until we get to end. WN. So it's a graph which just contains the single path that is the word. Right? Now, to give a map of cospans in, we take this, we first have to pick 2 elements of G, which we'll call, this would be the actual, like this starting and ending points in the boundary of G. So I'll call this G0, comma G1. And then to have a map here, this would be an actual trace of the word. As in, it's a sequence of edges. A homomorphism of graphs would be a sequence of edges, each of which is, all these homomorphisms are label preserving. So we get a path in G. It has to start at G0, because if we go from start into here, we get start. And then we go from here into here. We would have to do the same by the commutation of the square as going into here, which is G0, and then going up into here. So for example, if G0 was this one, and G1 was this one, then you could see that we are, in other words, from here to here. Then if our word was, for example, A, B, A, then indeed we would have a path, because we could go A, B, A, and that would go from, oh, that went to start. So that's not quite right. But so that wouldn't work, but I could do A, B, A, and then go back over here, and that would actually start at the start and end at the end. And so again, we see that the, of course, nothing has to happen on this side. That's sort of, it's all up to the right. So again, the point I want to make here is, again, this is in a cospan situation. Again, we have some kind of thing here, PW, start, end. And then over here, we have our graph. Sorry, that's not where the graph goes. The graph is the arrow. And then we have notions of this square here in cospans of graphs. of labeled graphs. So my point, my point is again that behaviors of systems are included in these double categories as maps. They're representable. But knowing that we're in the double category gives us more features, because in all of these cases, we can enact composition of systems by post-composing each of these on the right by more things in the double category. Now, of course, we generally want to compose multiple systems. Last time, as you saw, in order to avoid having to deal with that, we just used a unary composite, something like, for example, taking a trace, taking a feedback loop. But in here, this time I want to go over how we can have multiple composites. And the way we would do that is to note that all of these examples of systems are symmetric monoidal double categories. Right? Now, again, I want to emphasize that all of these examples here are examples of special kinds of span double categories. So remember that lens was span in vector bundles, or lens in here, vector bundles with vertical left leg and Cartesian right leg. And similarly, lens in sets, the ordinary notion of lens, or like, you know, Van Laarhoven lenses, etc. Lens in the simple fibration of set over set, again with vertical and Cartesian. I believe we went over this. And over here, cospans in graphs as a neat little trick. That is the same thing as span in graph over BL op. Just cospans are spans in the opposite category. And then we don't make any restrictions on the legs. Although I would note that if we wanted to, we could. If we wanted the legs to be monomorphisms, for example, which is actually pretty, if I say that this boundary, it's kind of nice for the boundary to actually be included in as a monomorphism. So we could do that. They are stable under push-out monomorphisms in free-sheet categories, which labeled graphs are.
It's span on vertical.
Yes, that's great. Thank you. So cospan is span the span graph category, and then we take a vertical opposite, which is or the tight direction opposite, because these maps go down. In the span version, they would go down in the opposite, which means they would go up. That's backwards. So we then op it again. So we op it in here, but then we have to op it again out here. That's right. Thanks. And so for this reason, I'm just going to talk about the monoidal structure on spans, and then we're going to specialize it to all of these cases. So knowing that we have this adequate triple formalism for the span construction, which I might go over again, we see that we can get a, we'll see that we'll get a monoidal structure on our double category. That monoidal structure will allow us to combine both systems, objects, and maps in parallel. So it will turn into a parallel product of systems. Okay. So recall an adequate triple CLR is a category C, two classes of maps, L and R, some classes of maps in C, closed under containing isomorphisms, including identities, and closed under composition. So you could say that they are what's known as a wide subcategory. And for any, I like to use my colored diagrammatics here. So the quantifiers are going to be in the order that we say this. For any where this is in R and this is in L, there exists a pullback like this, such that this is in L and this is in R. And for all pullbacks, we have that this is in L and this is in R. So there always exists a pullback. I guess I should say that I could say that there always exists a pullback, and any pullback has the property that if it was one of these pullbacks, that it's a pullback of L and R, that these faces, if this is an L and this is an R, then this is an L and this is an R. So from that we can perform. So from an adequate triple, what is an adequate triple adequate for? Of course, it has 3 bits of data. It is adequate to perform the span construction. That's sort of it. From an adequate triple, we can form a double category span CLR. And so a square like this in that double category is a diagram like this. It commutes, and the marked thing, the left legs of the span are in L, and the right legs of the span are in R. Yeah.
That second condition, does it not follow, sorry, this one, the, I guess, second condition, part 2, follow from the first one, given that there's always going to be an ISO between the 2 pullbacks. And if L and R are close in the composition and contain ISOs, then does n like numerically need to?
Well, that's rather nice. I think, yeah, that sounds right to me. There's it's rather nice to have it just contain all identities, and then I think you need the extra repleteness. But morally, it should contain all, like morally, no definition in category theory should be sensitive to the difference between an identity and an isomorphism. So yeah. That sounds right to me. Okay, so right. So now what I want to say is also that this construction, so span is going to give us a 2-functor from add triples to double categories. That's not a double category of double categories. It's just a double. So it sends a adequate triple CLR to span CLR. And if I have a map here, which is a functor, I'll call them LC, RC, LD, RD, this goes to span D, LD, RD. If this is a functor F that preserves, so it's a morphism in this adequate triple thing, so that F of LC is contained in LD, it preserves both classes. F of RC is contained in RD. And if we have a pullback like this, then F maps it to a pullback. F preserves the pullbacks. So this is the, as I would say, the quote unquote obvious notion of morphism for this data. It preserves all the things in the data, including, so it preserves both classes, and it preserves the pullbacks you're supposed to have for the classes. Then you can give this F gives you a functor like this, which I'll just call F again. And what does it do? Well, if I have this span up here, I apply F to it, and I get FA, FS, FB, FC, FT, FD. And that's just how it acts. And now, because it preserves both classes, this is still in L, this is still in R, this is still in L, this is still in R, but now we're in D. So I could label them all with D. And it's also got a preserved pullback composition of span, which I guess I didn't go over again, but it's given by pulling back over the middle things. If I have another one here, right, then I form the pullback to compose that. And I form the pullback down here. The universal property gives me a map like that, and that's how I compose. Well, these are RL pullbacks. So by hypothesis, F preserves those, and therefore it preserves composition. So this gives us a double functor. And then if I have a transformation between these two things, and it can be just completely arbitrary, I get a transformation again over here. But this is what's called just to be clear, this is a tight transformation. And what is it? Well, if I have F, S, F acts just component-wise on the span, like this. G also does. And I have a natural transformation tau. Well, tau gives me all of these. And these are all naturality squares. So they all already commute. And that gives me, as you can see, a cell here. FA, B, FS, to GA, B, GS. And that is the sort of thing we get with a tight transformation. And it does remain to check that this actually commutes with the pullback, but this follows by the universal property of the pullback. The uniqueness part of the universal property tells us that the composite of two taus is in fact another tau. Simply because there is one up there, and the uniqueness says that it must be. I'm not going to run through this. If you're wondering, you can look up this in, say, Grandis higher categories. Is that what it's called? Higher dimensional categories. I think that's what it is. Grandis's higher dimensional categories has a definition of these. I think he would call this a horizontal transformation because of his conventions. But we're calling them tight transformations to avoid this problem of the fact that we draw them going vertical, and when see over in here we draw them vertically. To avoid this conflict in terminology, we're going to call them tight because this direction will always be the tight one and this one will be the loose one. So I believe in Grandis it's called this if you want to look up all the laws. Okay, so this is a two-functor. Span construction is a two-functor, but also I claim that it preserves span. So let's say theorem, span is a two-functor. But it's also, and span preserves products. So span of C times D, LC times LD, RC times RD is equal to, or isomorphic to, really, span of C, LC, RC times span of D, LD, RD. Okay, so first of all, you have to check that this is actually the product in adequate triples, but that's not so hard, right? Because C times D is the product of categories, and with these choices for what the classes are, that is to say pairs where the left leg where both elements of the pairs are in the left class, pairs where both elements of the pairs are in the right class. That has to become an adequate triple, but that's okay because pullbacks in a product category are just taken in each component. So there's really nothing to check. And similarly, the product projections preserve these classes by definition. And to show that the universal property holds, you just have to show that if you have any two maps into one map into C and a map into D that preserve both classes in those pullbacks, they go into this one, you'll see that you're forced to take this definition of the product in adequate triples. So why does this work? Well, what is a span here, right? It's like A naught A1, S naught S1, B naught B1, where the zeros are in C and the ones are in D. And both the classes are in that. Whereas what is a span in this one? Well, it's something like this. And you can see that this is just the data. Again, these are pairs of maps. Are not, yeah.
One of those should be.
Maybe I should, yeah, maybe this is, yeah, sorry, I think.
Like that's L.
It should be L not L1, thank you. R not R1. L not R not L1 R1. There we go. And as you can see, we're just writing the data in different ways here. So for that reason, span is a tube functor. It preserves products, and therefore it will preserve pseudo-monoids. It will preserve symmetric monoidal objects. So let's go into what that is. So let's talk about symmetric monoidal categories. So a category is symmetric monoidal when it comes with a combination functor. It's usually written tensor, and a unit functor. Whoa. Usually written 1. And this, by the way, it's a functor from a one object category. So i.e., this just means 1 is an object. And this means that we can take any two things, A and B, and we can give the tensor product of them. Now, usually I will say that this is often a parallel product. For us, it will be a parallel product. It will be a non-interacting product usually. Right? That is not a mathematically defined term, I would say. Yeah. But that's how it, in all the examples we're going to use, it will roughly speaking be that, even though it will not always be Cartesian. Though sometimes it will be, often it will be. Okay, so what do these have to satisfy? Well, we need unity. So A, we want it to equal A, but again, we're in the same situation we were before. These are objects in a category. They shouldn't really equal. So this is usually called L or something, or lambda. I'll do it in Greek. This is called rho. And then we have the associator. We call alpha. And these have to satisfy the same laws we saw last time for the monoidal category, because as a usual examples is Cartesian product. Let's say of sets. Concreteness. And the one element set. So in particular, we have the one element set times any set. We need an isomorphism from that to the set. The elements of here are pairs of that one element and some elements here. The elements here are elements here. It's pretty obvious what to do. It's the same thing on the other side as well. Oh, I didn't do the symmetry. We also need a commutativity condition. And we didn't talk about the laws governing that, so maybe I'll want to say that, but maybe I won't, because again, for us, it's mostly just shuffling around parentheses. For the associator, of course, it's the same thing as we saw before. Again, A, B, comma, C goes to A, B, comma, C. And then we also have symmetry. Can you guess what's going to happen now? Now, for all these to make sense, they have to satisfy some laws as well. But those laws are all the ones you would get if you just looked at this reassociating and symmetrizing and asked that those held. So you can think of it as just being those. The symmetry is rather interesting because there are actually multiple non-trivial ways, non-equal ways to give laws for it, but they sort of organize into a hierarchy, and we'll choose the maximally symmetric version. But one step down would be you have this symmetry, but it only satisfies some laws, and that's known as a braided category. But again, we're basically taking true parallel product. So the order in which we multiply the systems really shouldn't matter. They're just sort of considered together. So yeah. E. Okay. All right. So what's a symmetric monoidal category? It has this kind of structure. An example is a Cartesian category, also a co-Cartesian category, where you have plus, say, graphs. I mean, graphs are also Cartesian, but we'll often use them this way, plus and empty set. Yeah. So now we have empty set plus is disjoint union or coproduct. Zero plus A is isomorphic to G. It's almost hardly worth mentioning. Although if you are a true formalist / you like formalizing mathematics in a computer, you'll note that there is something to do here. Nevertheless, it's sort of trivial. We've disjoint unioned nothing to our graph. That is surely the same graph. And in the associativity, again, we've disjoint unioned 3 different graphs. It doesn't matter which order we start disjoint unioning them. Okay. I will note that it's exactly as non-trivial in this case as it is in the labeling case. And maybe I'll go into that. Because if you imagine that each one of these picks up, to keep the union disjoint, you have to label the names. So if I go in here, I have my 0 and my 1, and I label these things in G0 and G1, but elements in here are either of the form G1 and G2. But you see, the labels I add to make sure that I know which half of the disjoint union I'm in will be exactly associated in here on this one. So for example, just as I mentioned before, if you're actually labeling these and you're keeping track of these labelings, which you must be when you're representing these on a computer, the problem, the minor difficulty of shuffling around parentheses is precisely recapitulated dually with the essentially addresses for getting at the elements of these disjoint unions. And then again, the symmetry, of course. But on the other hand, in the picture, you imagine a disjoint union being just like you put them two together and they don't touch. Well, of course you can throw as many you want together in whatever order you want together, and they just sort of move around each other. They don't touch. Okay. So these are our examples. So now we can talk about what is a symmetric monoidal double category. Well, you'll be happy to hear that it's basically the same thing as a symmetric monoidal category. We have these double functors now, and they satisfy the exact same laws, which I'll just pull from here because I'm lazy. Although we must say what these mean now, a little more in a little more detail, so we will. Right, so we have these same things, but now let's think about it. Well, this is certainly true for objects. We need these isomorphisms for objects, but remember that we're in the double category, so let's remember that this would be written vertically in our conventions because they are tight isomorphisms, tight transformations. So all of the laws here, I guess I didn't mention it above, but all of these laws have to be natural in the category case for symmetric monoidal categories, and for symmetric monoidal double categories, they need to be tight natural transformations. So we would have one tensor A to A, but now we can also have a double theoretic aspect because I can also take one tensor some loose morphism L to one tensor B, and then I have this goes to B here, and now I have my original L here, and we also want that there be a cell which is invertible in the tight direction. And again, what that means is that by stacking these boxes on top of each other, they would cancel, right? So in other words, one tensor L to L to one tensor L, and then these have two sides of the boxes right here. This is going to equal one tensor L identity one tensor L, and the other way around. Similarly for all of the other ones, right? So that's really the addition here, the extra feature we've had. So now here's the thing to note is that in here, this example, this is what's called a symmetric monoidal double category, is what's called a symmetric pseudomonoid. In cat, the two category of categories. So what is pseudomonoid? Well, a pseudomonoid is just a monoid. As you can see, we have structure that looks like a monoid. We have this binary multiplication. We have this unary identity. So we have a multiplication, an identity, a unit, and then we have unit laws, and we have associativity, and we have symmetry. right? But all of those only hold up the isomorphism, and so we say it's actually pseudo. But note that in order to say that these held up the isomorphism, in fact, natural isomorphism, we needed the idea that maps can have isomorphisms between them, which is what it means to be in a two category. So maps can have isomorphisms between them in cat because functors can be naturally isomorphic. And precisely what we're saying here is that all of these functors are naturally isomorphic to each other. Okay, so a symmetric monoidal double category is a symmetric pseudomonoid in double categories. And that's the right definition. In fact, a symmetric monoidal anything is a symmetric pseudomonoid in anythings, right? This is a very nice trick which tells you how to generalize the idea of symmetric monoidal or parallel product to unfamiliar settings, right? If they form a two category, then it makes sense, a Cartesian two category, to have products, right? We have to have these meta theoretic products in order to write this down. This is what John Baez called the microcosm principle, or Baez and Dolan called the microcosm principle. We need a monoidal two category, namely the Cartesian product on double categories, in order to express a monoidal category, or in this case, a monoidal double category. Okay. So, all right, let's say that, so we'll define a symmetric monoidal adequate triple is a symmetric pseudomonoid in the two category of adequate triples, which we've already seen is Cartesian. What does that mean? I.e., we have C, L times L, R times R, sorry, C times C, whoop. To C, L, R, and one, I mean, there's only one arrow in the one object category with one object, into CLR, which this will be called tensor, and this will be called one. So plus the natural transformations, but the natural transformations, so plus natural transformations. Oh, right. Lambda, rho, alpha, giving the laws above. So what does this mean? Well, first of all, notice that this is in particular, this is a symmetric monoidal category because the morphisms of adequate triples are functors that satisfy certain properties, and the two cells, the transformations, are just natural transformations between those functors with no extra criteria. So in particular, this is just a symmetric monoidal category, but there's two extra facts, which is that both tensor and one are morphisms of adequate triples. Now, one being a morphism of adequate triples doesn't say anything about it because there are no pullbacks in the category with one object to preserve. But tensor being does say something. So tensor being a morphism of ad triples means that if I have two squares like this, oh, I'll do it like this. Yeah, I guess. A naught, B naught, C naught, D naught, and A1, E naught, D naught, C. Oops, those are all ones. And the left leg here is in R, always. And the right one here is in L. Always get that wrong. It's the direction they're pointing when you draw this. Okay. It's an L, and these are both pullbacks. Then, so if these are both pullbacks and those conditions satisfy, then their tensor product is also a pullback. That's just what it means for tensor to be a morphism in this two category. So A naught tensor A1 to B naught tensor B1 to C naught tensor C1 to D naught tensor D1. So these in particular, these are still in R and L respectively. So the tensor product has to preserve both classes, very important. And it has to preserve these pullbacks. Right. So, right. So let's recall, let's see that this actually gives us some symmetric monoidal source. So if C has pushouts, then C op all is an adequate triple. Right? Why? Because pushouts in the opposite, when you take a category with pushouts and you opposite it, all those pushouts would become pullbacks. And that's what we need for an adequate triple. We need pullbacks. Of course, we could do the whole theory with adequate triples for pushouts and take a cospan construction, but this is just going to allow us to avoid reduplication of effort. So now, if C also has an initial object, then it has all coproducts. Because the coproduct of A and B is in fact their pushout over the initial object. So in this case, we can check, we have that C plus an empty is a symmetric monoidal adequate triple. Smat. So why is that? Well, we need to check this one extra law here. And what does that law say? Well, I'll write it out here, but I'm going to write it. Remember, we're in the dual, so all the arrows will go backwards. This is a push out. A1, B1, D1, C1. Push out. Then we need that, well, what is it? It's plus. So there's nothing to check about L and R because we said that all maps are there. We just need to check that if you have two pushouts, their disjoint union is a pushout. And it's just not hard to check this by looking at the universal property of pushouts. You could also check it by using a version of pushout pasting. By the way, the same reason gives you that if you have a Cartesian category, if you have a category with all pullbacks and a terminal object, it spans, then it will be a symmetric monoidal adequate triple. So similarly, if C has pullbacks, then C all times 1 is a symmetric monoidal adequate triple. Okay. Therefore, for span of C all is a symmetric monoidal double category. And remember that this is cospan of C, like all. Oh. And I'll note that the laws of a symmetric monodal double category are tightly dual because everything went in the tight direction. All the laws went in the tight direction and they were all invertible. So if some double category is a symmetric monodal double category, its tight opposite is also a symmetric monodal double category. The opposite is a two functor that preserves products. That's another. So why? Well, remember that span preserved products. So if I have, say, something like C tensor C up times C plus C, then I get span C up times span C up to span C up. This is plus as well. And for all the laws. So let's look at what this actually means in the case of labeled graphs. Okay. So now we've deduced that labeled graphs, cospans of labeled graphs, in particular, cospans of labeled graphs is a symmetric monodal double category. Under using with plus and empty. So as you can see, right, if I have, so given a labeled graph with boundary, which looks like, again, a cospan of this form, which I'm going to write like this. To G. So given two of these, I can form their sum. And I'm writing it in the other notation over here, just so you can see what it looks like in the abstract. Right? Yes.
DH and the boundary meant the second.
Thank you, Cheyenne. All right, DH. Okay. Right. So what does this look like? Well, if I have, some graph up here, some graph over here, this is G, this is H, this is G plus H. Right? That's just what the disjoint union does for the pictures. Now, also, you'll note that we ended up with this empty plus empty. And anyone who's formalized mathematics, which I have, you can hear the pain in my voice. I do. It can be fun. Knows that actually empty set and empty set plus empty set are not exactly the same set when you formalize. So we note that there is in fact an isomorphism here to empty set and here too. The opposite of an isomorphism. Isomorphism to empty set. So really what we're going to take to be the composite is this thing. These two empty graphs, because this is something you don't have to worry about too much unless if you're formalizing things. But once you have spent time formalizing, you develop a second sense for all of these nasty little inconveniences, which I'll let you think about what you need on a double category in order to do what I just did. Because it's not, because if you remember, all our isomorphisms went in the tight direction, but I just stuck an isomorphism in the loose direction. So we might come back to that later, because actually that being able to do that actually turns out to be a technically very useful property later on, but I'll just say, don't worry about it yet. Right. Okay. So there's our disjoint union. But also, of course, we could do this for anything. So suppose I had some other new kind of graph here. And this was some kind of composition pattern. This was some other one. Then, of course, I would also get something like this. That could say, for example, glue these graphs together. Let's give an example of that, right? As we discussed, I believe we did actually discuss this earlier. We could imagine that our graph would be in a box with some wires out, and our graph could have these wires connecting up to two of the nodes. And then there maybe are other nodes, and there's a graph like this. And then we would have another one out here, right? For example, this one, and it was connected out to this wire. Maybe this one was connected out to this wire. And then these were also a graph. And now I could take this and I could wire them together like so. And maybe I don't pass this one out. Something like this. What is the outer one here? So remember that we went over how you could compose this. I believe we did in this lecture series.
Maybe for labeled.
To label transition systems.
Yeah. Yes, I guess it's sort of the DG and DH, DG prime, DH prime, WW prime. I guess we're assuming they're all like sets and maps of sets here, which they don't need to be.
Yes, they don't need to be, but this would at least work. So in here, right, we would say that this is G plus H. So and here we have the boundary here is boundary of G is these two things. If I call this A and B and this C and D, is A and B plus C and D as the boundary. This wiring diagram out here, I can call X. Suppose that this wire calls X. And then in the middle, I'll put these three junctions, J1, J2, J3. And now the wiring diagram itself gives me a cospan like this, where I take this maps into here, this maps into here, this maps into here, this maps into here, this maps into here. There's nothing to map into that. I take the push out over here in graphs. And this is how I might get a, excuse me, I suppose I don't want to do two at the same time. I want to show you how you will pose like this. The composite, after we take the disjoint union, and then we take this wiring diagram and we compose them, and the result will be something that fits in this big box and has a single wire coming out, right? And then we draw in the inner ones. However, we have taken these two and we've glued them together. So there's actually only one in the middle there. And then we have our other dots here. And this is the one that goes out. So now we've seen how we can wire together our cospans. I think I covered this in a different lecture and not in this series. So sorry for everyone following along. I'm going to do that again tomorrow.